On to the next example, example 3. I just wanted to recap. My battery died, and there were a couple things that I wanted to say yet. One of them being that with the approximate area, recall that we had 6 subintervals, and we got an estimate of what the actual area would be. And when we came to b, we took the limit as n, the number of subintervals, went to infinity. We obtain the exact area. Though they're a little bit, the first one is a little off. It's still negative, and it's a couple away from, or almost 3 away from the exact. But it's still giving us an idea that the area will then become more negative than positive. So let's move on to example 3. Example 3, we want to just set up an expression for the integral from 2 to 5 of x to the 4th as a limit of sums. So the first thing for part A that I want to do is I want to say, okay, for part A, we're going to say, what is f of x for this? F of x is then x to the 4th. So f of x is, or why don't we just say f of x is equal to x to the 4th in this, x to the 4th, as we're looking at the integral from a to b of f of x dx, the definite integral. Okay, so just want to get that out there again. So we have the function, and then we'll say, well, what is the lower limit? A is equal to 2, b is equal to 5. So that means that delta x is equal to b minus a over n, and let's see, b minus a, so it would be 5 minus 2 over n, so delta x would then be 3 over n. Now it's not always, we've had a couple of examples where delta x was 3 over n now, but it's not always going to be 3 over n. So we'll do then x sub I. X sub I is, remember, it's a plus I times delta x. So where we're starting, that would mean that x sub I would equal 2 plus I times 3 over n. Okay, so we have our x sub I. And let's see, what else do we need? I think that is about it. So we have our f of x sub I that we'll need for our Riemann summation, which is, remember, x to the 4th. So we take our x sub I, 2 plus, and I'll simplify this, 3i over n, and that will be to the 4th power. So that our Riemann sum, the summation, I is equal to 1 to n, and we will be taking the limit, so why don't we say that instead? So we have then the integral from 2 to 5 of x to the 4th dx will be equal to then the limit as n approaches infinity of the summation of, from I is equal to 1 to n of this quantity, 2 plus 3i over n to the 4th power times delta x, which is 3 over n. Okay, so now this is what we want, but recall that the rule is the integral of f of x dx from a to b is equal to the limit as n approaches infinity of the summation from I is equal to 1 to n of f of x sub I delta x. So you see that we've got all of the necessary information in our summation. Okay, so now we have set up an expression as a limit of sums. Okay, we've done that. The second part of this, we want to get the answer for our integral. We want to evaluate the sum with our calculator. So we're going to move over. We're going to say, okay, we want the integral from 2 to 5 of x to the 4th dx. We want to get a value for that with the integral. In another video, we will be dealing with taking the limit of a sum as n approaches infinity. But for this part, what we're going to do is we're going to evaluate this with the calculator. And so we're going to move over to the calculator now. And what we're going to do, the first thing we're going to do is I go to y equal and put your function in x to the fourth. Once you put the function in, we want to get a decent window for this. And remember, we're going from 2 to 5, and 5 to the fourth power is 625. So if you look at the window that I've chosen, I leave the negative 10 to 10 and the scale of 1 for the x values. But when I come down here to the y's, I put the y min at negative 100 and the y max at 645. So I've gone beyond both the minimum and maximum values that I'll need. And I put the y scale at 50. And I turned off the grid so I wouldn't have to deal with, the grid on the graph. It just detracted from everything. So now here we go. The steps that we're going to use then, let me move this up just a little bit so you can see some of the steps as they come through. And so what we're going to do then, let me clear this part off so that, okay, now we're going to hit second trace, and I'm going to hit 7. If you notice, we have the integral notation down here, 7. And then I'm going to hit the lower limit of 2 and the upper limit of 5, and then hit enter. And I get the area is 618.6. And you see that down in the lower left-hand corner, and it says on the interval from 2 to 5. So we'll go back to our notes. And by the TI-84, you may have a Casio, or maybe you have an 83, but it should be similar steps here, would be 618.6 would be the answer. So a definite integral will be a number if you have numbers in the lower and upper limits. So here we go. We'll move on to example 4, where we evaluate the following integrals by interpreting known geometric areas. So if you look at the first one, it's the integral from negative 2 to 4 of x plus 2 dx. So what you're looking at is negative 2 to 4 on the x-axis for the limits all along the x-axis, and the line is y is equal to x plus 2, but I'm only going from negative 2 to 4. So what I'm going to do is I'm going to draw a line from the curve x plus 2 down to the x-axis. And so the area captured would be triangular. And x plus 2, the height would be 6. And the base from negative 2 to 4 would also have a measure of 6. So the integral value in this case is geometric. And we would have a value of 1/2 6 times 6, 1/2 the base times the height, or we would get 18, and sometimes we say 18 units squared, but we'll just leave it at the number at this point. But it is the area under the curve between the x-axis and the curve. So let's look at the next one. We have the equation, the square root of 16 minus x squared. And if you recall, when you see this, if you make this y is equal to the square root of 16 minus x squared, recall if you square both sides, you would get this. And then you remember your study of trigonometry where, oh, you're dealing with the unit circle and you have x squared plus y squared is equal to 1 squared. And you know that that's the unit circle, and this is just the circle centered at the origin with radius of 4. So just so you're familiar with this particular integral, it comes up so much in the AP exam as well, the square root. So what we do is we look at the geometric area that is under the curve. So I'm going to shade it purple here. So we're going to shade that, and we're just going to say the value of the integral then is 1/2 pi times 4 squared. Now, let me say that the area for a circle we know is pi r squared. So also the area for a triangle then is, of course, 1/2 base times the height, just in case you need to be reminded of that. So in the second one, then it looks like we get 16 times 1/2 is 8. So this value is, of course, 8 pi. And they would be square units if you wanted to say the units with it. Okay, so in the next example, we're going to be dealing with something called the midpoint rule, and I mentioned it briefly before. So we're going from 1 to 2. So my A is 1, and my B is going to be 2. So the first thing I do when I look at this, you have this integral. We're going to use the midpoint rule with this. We're going from 1 to 2 of 1 over x dx. So I'm going to say that that's approximately the summation from I is equal to 1 to n, I'm going to leave the n off, of x, and I'm going to call it an x bar, f of x bar times delta x. So in this particular expression, I'm going to first take an aside over here, and I'm going to say, well, what is delta x? Delta x is equal to 2 minus 1 over, and it looks like we have 1, 2, 3, 4, 5 subintervals on the partition. So we end up with a 1/5, or you may use that as 0.2. So here's our delta x value, 0.2. And it's the same for all the subintervals. So now what we're going to do is I have to look at all the subintervals, and sometimes I do a lot of work off on the side when I handle these. I say, all right, if I'm going from 1 to 2, or I'm going to start here, and I know I'm going to go 0.2 to the next subinterval, and then I'm going to go 0.2 again, so 0.4, and go 0.2 again, 0.6, so 1, 2, 3, 4, I have one more after that, so 0.8, and then we have 2. So that would actually be 1.2, 1.4, 1.6, 1.8, and then we get to 2. So you see all your delta x's. So I want this middle value for x. So that middle value then from 1 to 1.2 is 1.1. These are x values now, remember. These are the x bars that I talked about. So I've got 1.1, 1.3, 1.5, 1.7, 1.9 are the x values that I will use in my summation. So I'm going to have the summation from I equal 1 to 5 of that. So I'm going to say that this is then approximately equal to the summation from I is equal to 1 to 5 of f of x bar times delta x. So now here we go. Remember that we can factor out the delta x and multiply it at the end. So we just add up all the f of x sub bars and then multiply by delta x. So we have the following then. This is then equal to, so I have f of 1.1. That's the first one, if you can see down here in the corner, lower left-hand corner, plus, oh, better put a bracket in here first, f of 1.3 plus, move down here, f of 1.5 plus f of 1.7 plus f of 1.9. So those are the function values I'm looking for. And then I'm going to multiply in the end by delta x, which is 0.2, or if you're using 1/5. So we get the following. Remember, this is the function y is equal to 1 over x. So we get that this is equal to the summation from I is equal to 1 to 5 is, and I'm going to be a little brief with this, leave some 3 dots here, but that would be equal to then 1 bracket 1 over 1.1 plus 1 over 1.3 plus, here's the function values, 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9, put a bracket here, and then we would multiply by 0.2. We add that up. Using a calculator, we get 0.691 908 units. Pretty small little area, right? It's not huge. Using the summation, we get this is approximately the integral from 1 to 2 of 1 over x dx. We'll take a look at that later. So what you have are some properties then. Let me move the erase a little bit here. If you go to page number 333 in your textbook, I think it goes on to 334, some properties that you will need to know. If you're taking an integral from a to b, it's equal to the opposite of the integral from b to a of f of x. There are times where it's convenient for us to switch them, but it's just a rule. If we take the integral from a to a of f of x dx, we get an area that is 0. We don't have an area. Think about that. There is no value to the integral. If we take the integral from a to b of c, I think this is just a constant. Here, I'll draw a little graph of this. If we have a y is equal to c graph, and we're going from a to b, let's block that area off. And you notice that it's a rectangle, right? And it has a base that's b minus a, and of course the height is c. So for this one, it's just going to be c times b minus a. Easy to calculate. If we have in number 4, if we have a constant, we can pull that constant around front and say that's c times the integral from a to b of f of x dx. And then for the sum and the difference rule, maybe not all of the time, but you will come to a time where you will come to a specific set of integrals where you are going to want to split the integrals. And so it's important to know that you can do that over a sum. So this integral of the sum of f of x plus or minus g of x is equal to the integral of f of x plus or minus the integral of g of x. So in Calculus 2, that will become a very important concept because you'll have to integrate 2 different ways. So hang your hat on that one for Calc 2. Okay, before we get to example 6, I'm going to stop this video, pick back up at that, and we'll recap what we just finished.